So we're in section 4.1, part 2. Talking about arc length and angular speed. All right, so remember from last time that we said that radian measure, theta in radians, theta is the arc length, S over R. So arc length over the radius. That's how we defined the radian measure of an angle, the arc length divided by the radius. We said because of this, since both arc length and radius are measures of distance, measures of length, radians don't have any units. Makes them convenient to calculate with because you don't have to convert units with radians. Well, if I multiply both sides of this equation by r to get the arc length by itself, I can say so the arc length is r theta. So if we know the radius and the angle that we've rotated through, that's going to tell us the arc length, the distance that the tip of that angle ray has traveled. And I want to emphasize this is for theta in radians only. So this, when we calculate arc length this way, our angle has to be in radians. Now, if you remember back to geometry, you had a formula that calculated arc length around the circle, and it probably had your angle over 360 that it multiplied this and that. That angle over 360, what you did for that equation that you learn in geometry is you convert your angle in degrees to radians. You just didn't say that's what you were doing. But that's what that formula that you might have learned for arc length in geometry does. It converts the angle in degrees to radians, and then you calculate the arc length with it. So this is our first big formula for today, for this section. The arc length equals the radius times the angle in radians. So an example, I'm going to want to do an example of the kind of problem that you might see that has to do with arc length. The way the book asks a question, the book asks these questions in kind of a convoluted way. And then I want to show you, we won't work through everything, but I want to show you another example where students sometimes get confused about what to do. So the first example, the kind of convoluted book language. The problem might ask you, find the length of the arc that subtends an angle of 120 degrees in a circle of radius 5 inches. So what this question is asking, I'll draw a little picture here. Here's my circle. I have an angle. I've moved on that circle through an angle of 120 degrees. The radius is 5 inches, and they're saying find the arc length. So they want to know how far have you traveled along here. That's what that problem's asking us. That's kind of translating the language there. That's what it's asking us. All right, so what's the first step? What's the first thing we have to do? Yeah, we need the angle in radians. So 120 degrees times pi over 180 degrees equals, didn't we do this the other day? 120 over 180 is 2 pi over 3. And we can leave the radians off because radians don't have any units. So our arc length, now we have our angle in radians. So S equals 5 inches times 2 pi over 3 radians. So I get 10 pi over 3 inches. That would be my exact answer. And that's approximately, if you plug that in your calculator, 10.47 inches. So that's what that question is asking us to do. All right, questions on that example? All right, let's look at an example that seems more confusing, but it's really not. So this one, I'm just making up these numbers. So we have two cities. One is due north of the other. One has latitude 37 degrees. The other has latitude, I don't know, 85 degrees. The radius of the Earth is about 4,000 miles. How far apart are the cities? So looking at that, it seems kind of complicated. Well, let me draw a picture. So I'm going to do a side view, kind of do a cross section side view of the Earth. So there's our Earth. Here are these two cities. One is at latitude 37 degrees. One is at latitude 85 degrees, almost at the equator. One is due north of the other. There's the North Pole. There's our North Pole. So what is this question really asking us? Let me draw in a couple of other things. There is the radius of the Earth. There is the radius of the Earth. (4,000 miles). So what is this question asking us to do? The distance between the cities? What is that distance? Just in not the value of it, but big picture. What is it on this drawing? It's the arc length. It's asking us to find the arc length between those 2 points. So a question like this is really asking, find arc length. That's why the cities have to be due north of each other. Well, what does this 37 and 85 tell us? Well, if this angle from the North Pole to here is 85 and this angle from the North Pole to here is 37, can't we figure out this angle? Yeah, what do we do? Yeah, we subtract. This is 85 degrees minus 37 degrees. And then we have exactly the problem that we just did. It's just a slightly just different numbers. So we did the calculations on the last one. You can go through here, but this is just asking us to find the arc length. We convert this angle, whatever we get when we subtract those two, convert that to radians, multiply it by the radius, and we'd have the distance between those two cities. So don't worry when you see a problem like this. Really it's saying find the arc length. And they'll ask the question, these arc length questions in a bunch of different ways. You'll have maybe a needle on a scale, a needle on a meter, something, and it's some kind of situation where it asks you to find some piece of that equation that has to do with arc length. All right, so questions there? All right, let's talk about angular speed. So I'm going to start with our equation from before. The arc length equals r times theta. And we know, or I'll tell you, that the speed that something moves is distance divided by time. Miles per hour, feet per second, kilometers per hour. So our speed is distance divided by time. So I'm going to divide this equation by t, time. So I get s over t, which is some distance over time, some speed, equals, if something's traveling in a circle, we're saying the radius is the same, and I'm going to say theta divided by t. So we're dividing both sides of the equation by t. We call this s over t, that's just distance divided by time, the linear speed. So if we're talking about your bicycle going forward at 15 miles an hour, that would be this, the linear speed, 15 miles an hour forward, equals the radius, and we call this the angular speed. Theta divided by time. And that tells us a point on the wheel of your bicycle, how many radians it's moving through per some amount of time. So if you're going 15 miles an hour, it has to do with how many radians a point on the wheel of your bicycle is moving through every hour. Yeah.
Is the time under radians also, or like under r?
Well, we could put this like that.
Okay.
But we're thinking that the radius stays the same. We're talking about something moving in a circle, so the radius doesn't change in time, but the angle is going to change in time. So that's why I just put it under the one. We give these two things new symbols. So we say V equals R omega. And it comes from starting with our arc length formula and saying, okay, what if we're moving? What if things are changing in time? The units on our linear speed are going to be something like miles per hour, feet per second, etc. The units on this are radians per hour, radians per second, etc. So the radians per second, radians per hour gives us a measure of how quickly something is moving in a circle, how many radians it's moving through every unit of time. It's moving through 500 radians a second. It's spinning around pretty fast. And that will relate to how fast we're moving forward by that equation. If you have a tiny little wheel on the skateboards that people like to play with on their desks, that's rotating at 25 radians per second. Well, that tiny little wheel, if it's rotating 25 radians per second, doesn't mean the skateboard's going very fast. But if you had a huge wheel on a giant construction vehicle that's going 25 radians per second, it's going to move forward a lot more quickly because the radius is bigger. So that's what that relationship is telling us. So this is our second big equation for today. V equals R omega. So what I want to do is go through a couple of examples of applying this V equals R omega. Really, the kinds of problems that you'll see that we do with these are really a variation of one problem. They're kind of the same problem with different numbers plugged in. But I want to show one going this way from the omega to find the linear speed, another from the linear speed finding the angular speed, just to show the process. And often with these problems, part of it is converting units. So we'll talk about that when we do our examples as well. All right, so let's take a look. An example of this using this equation. So let's say we have a saw blade, circular saw blade. That rotates at 2400 RPM. So RPM is another common way that you'll hear about a measure of how fast things rotate, RPM. This is revolutions per minute. We want to find the angular speed. Linear speed if the radius is 4 inches. All right, so revolutions per minute related to angular speed, but it's not quite angular speed because our units for angular speed, and I'm going to say we want our units to be radians per second and inches per second for those two. So the revolutions per minute is related to the angular speed, but our units of angular speed are going to be radians per minute, radians per second. So let's find omega first, because this number that they give us is related to omega. The way I think about this is, and especially with with these problems, I think of the units as fractions. So I'm going to say 2400 revolutions per minute. How many radians are in one revolution?
6.
6, and so a little more exact, 2 pi. So I'm going to write this omega equals 2400 revolutions per minute times 2 pi radians per revolution. And I'm thinking of these units canceling out. So this calculation cancels out my revolutions, and I get 4,800 pi radians per minute. And then I want to convert that to radians per second. So I'm going to say times 1 minute. I want the minutes to cancel out per 60 seconds. I want the seconds on the bottom. So this way I don't have to think, oh, do I multiply, do I divide? I think about the units. So this is going to get rid of my minutes. And 4,800 divided by 60 is 80. Pi radians per second. So there's my omega. And usually you'll see this written as just 80 pi per second, because the radians don't have any units. I put the units in there just so we can think about the units as fractions. 80 pi per second would be the angular speed. So the edge of that saw blade is moving through 80 pi radians every second. It's quite a bit. Well, now that we have omega, we can find v, find our linear velocity. V equals our radius, 4 inches, times omega, 80 pi per second. So this is going to be 320 pi inches per second. And if we calculate that out, that's about 1,005 inches per second. So a little 4-inch saw blade rotating at 2,400 RPM, which is not, the saw blades rotate pretty quickly. The point on the edge of the saw blade is going about 1,000 inches per second. That's quite a bit. Oh, I said fin V. Find V. All right, so questions on that process. So you'll see problems, the problems that you'll see in your homework, some variation of this. There'll be something that's moving in a circle, you'll get some information about how fast it's turning, and it'll ask you some other information about that thing. Similar to doing this. Just same problem with different numbers. All right, I want to look at another example going the other way, going from linear speed to the angular stuff. So let's say for this one, we have a car. And we're going 65 miles per hour. Our tire's radius is 15 inches. We want to know how many RPMs are the wheels rotating. So 15 inches, not a super compact car, but not a huge car either. Kind of normal size car, 65 miles an hour. We want to know how many RPMs the wheels are spinning. And if you buy tires, when you eventually have to buy tires, the tires often are spin rated, so they're good up to a certain number of RPM. All right, so a couple of things about this. Our units here, miles per hour. Our radius is in inches. And we want our answer in revolutions per minute. So we're going to have to do some unit conversions. So I'm going to convert the velocity from miles per hour to inches per minute first. So I'm going to convert 65 miles an hour to inches per minute. So V equals 65, and I'm going to write this as a fraction, miles per hour. I don't know how many inches are in a mile, but I know how many feet are in a mile. How many feet are in a mile? 5280. Yeah, we live in a convenient place to remember that. So I'm going to say 52 times 5280 feet per mile. I want to cancel those miles out. So now I have feet per hour, and now I need to convert to feet per minute. So I'm going to say times 1 hour per 60 minutes. And now I've canceled out those hour units. And when I multiply this all out, multiply and divide, I will have my units in feet per minute because I've canceled out the other units. So when I do this arithmetic, I get 68,640 inches. Oh, no, that'd be feet per minute. Now I need to convert to inches, don't I? I forgot one conversion. What I was starting to write down was in inches. Now I need to convert to inches. So I need my inches on top. So I'm going to say times 12 inches per 1 foot. Then we'll have all the units canceled out. And my units will be inches per minute. And that's the number that comes out to 68,640. And I know that in some science classes you do the unit conversions in a nice little chart, kind of a horizontal grid. That's fine also. I just think of them as fractions, just the way I do it. All right, so there's our velocity. Well, revolutions per minute, like we said last time, are related to the angular velocity. So let's find the angular velocity. From our equation, I'm just looking at this one, omega is going to be V over R. I would divide both sides of this equation by R. So omega is V over R, which is 68,640 inches per minute, divided by 640 inches per minute, divided by 15 inches. And the inches cancel out here. And I get that our omega is 4,576 per minute. And we're implying that that is radians per minute. So 4,576 radians per minute. A point on the edge of your wheel is rotating through 4,500 radians every minute. Well, radians per minute is almost revolutions per minute. So we're going to use the same conversion that we did before. So I'm going to say 4,576 radians per minute. And we want revolutions per minute. So I'm going to say 1 revolution per 2 pi radians. My radians cancel out. And I end up with revolutions per minute. So I divide this by 2 pi. And I get about 728.3 RPM. So 15-inch wheel going 65 miles an hour is rotating about 730 revolutions per minute. That's why living next to highways is so noisy. Those wheels are traveling really fast. So problems that go from linear speed to angular speed, some kind of variation of this. Converting units, and often converting from omega, radians per second to revolutions per second or something like that. Some people like to think of this conversion from radians per minute to RPM having to do with the circumference of the circle, and that's where you get the factor of 2 pi. That's fine if you think about it that way. I always just think of this, I always just use the conversion 1 revolution per 2 pi radians. That's just the way I think about it. But if you think about it a different way, some students think about it in terms of the circumference, that's fine. All right, questions? Okay. Oh, and we already did, they told me last class, we already did 87 in the last homework, so I'll say 89. And these problems, the 100s problems, are going to be your arc length and angular speed word problems. All right, there you go.